This is a short introduction about the winding process of the superconducting shield septum prototype magnet at Wigner Research Center for Physics. Hopefully this will be the first video in a series, if I manage to keep it up. We have an exotic shape of the winding, and this S-like curve makes the winding process quite difficult because the wires tend to pop out of the groove here at this point due to the inflection point here. This made it necessary to use this tooling. It's a plastic Delrin tube with a window so that we can put it onto the shaft of the winding machine and slide it onto the former to keep the wires everywhere inside the grooves so that they don't come out. These tubes were made from Delrin, and when we removed this segment, due to the internal stresses of the material, the diameter jumped to a smaller diameter. So this part doesn't fit anymore, even though material here and here was removed. Therefore, in order to be able to slide it onto the tube, we had to machine slots into the wall so that we weaken it and make it possible to elastically enlarge the diameter. This segment that was cut out also deformed this way, so there is a significant few millimeters gap here. So this part cannot anymore support the wires in the grooves. So we decided not to use these parts and leave this window open here and keep these tubes always aligned with the easy part azimutally of the winding, where the wires don't come out easily. So these two tubes do not rotate, they're always like that. They slide up and down only, following this part, which is rotating around the former, because we are winding through this window here. So here we have put back this segment here and here on both sides, so that the wires are everywhere, azimutally everywhere, supported in the groove. Even though these C-shaped tubes have some elasticity and they have a smaller diameter than the former, their strength is not sufficient anymore, so we add these cable ties. The tightness of this tool is regulated by these bolts. So it should be tight enough not to let the wires come out of the grooves, but at the same time allow easy rotation and sliding of this part as we are following the winding process with this window here. During the development of the tooling, we also had a tube made of Teflon, machined to the right diameter inside and then cut into half. And this piece did not jump to a different diameter, whereas Delrin did. This is the winding tool that keeps the 2x5 wires aligned and help to get it into the groove. So it's made of Delrin as well. And there is a sheet of Kapton in between the two halves so that it keeps 5 and 5 wires separately. And you can load it, first assembling it, and then inserting 5 wires on one side and then 5 wires on the other side. The end of the 10 superconducting cables is connected together using household electricity quick connectors, easy to release and easy to connect, so that we can test their insulation against the former simultaneously, quickly. Once we find a problem, then we remove the cables one by one and test them one by one to identify which one is the problematic. That's the high voltage tester. At the beginning, we used the B pair, which was fixed here on the shaft with the tape so that we can immediately see if there is a short circuit. But it didn't seem to be too useful because at the beginning and while practicing we had several short circuits, and it only showed up when there was high voltage, but it was not a direct short circuit. So this device did not beep and it was not really useful, so we just removed it. And since we have very sharp edges of the grooves, we test the integrity of the insulation after every turn. That makes the process quite slow. So this is a high voltage test. This wire goes to the former. And these are the 10 superconducting cables. Now on this former, we have already about 65 turns completed. At the beginning, the reading goes much faster to above 200 gigaohms, the limit of this device. So far, whenever we had a spark, the damage of the insulation, it sparked immediately at the beginning. So you don't actually need to wait for the reading to reach 200 gigaohm. We test for 2 turns, we test it just pushing the high voltage test button, and if it doesn't spark, we continue winding. And then every 3 turns, we wait until the reading reaches 200 gigaohms to make sure there is no problem. There it is. Don't forget to discharge.